So yeah, today I would like to talk about computational natural language understanding with two different use cases, the use cases of life sciences and biology. So this is the first time I give an inaugural lecture, so I just want to make explicit what I think this is good for. So I would like to introduce myself to colleagues. With colleague, I mean students, faculty, and particularly, of course, also outside of IMS, because people inside of IMS might know already what I'm interested in. So this also influences a little bit how I explain things. And then, of course, I would be very happy if there might be potential collaborations coming up with somebody. So in any case, of course, if you think something would be interesting to talk about, please contact me. So Mr. Beroth already introduced me and where I've been, but I still want to go over this because it seems that it must have been destiny that I eventually arrive in Stuttgart. Yeah? So I studied computer science in Dortmund with a minor in psychology, then did my thesis on automatic composition of music with Günther Rudolph, who's actually also here, and it makes me very happy. And then I moved to Fraunhofer to do my PhD in biomedical text mining and machine learning. And this was the first time Stuttgart actually came into my life, because we once had a project meeting in Stuttgart. That was the first time I've been to Stuttgart. Then I've been to UMass Amherst, a very nice university with many very nice buildings, except for this one. That's the campus center, which is very prominent in the middle of the center. And it turns out that this building has been designed by Marcel Breuer. I'm not sure who of you knows Marcel Breuer, but Marcel Breuer also designed furniture in the UNESCO World Heritage Site of the Weissenhof Estate in Stuttgart. So there's another link. However, I found this castle at the Fraunhofer campus in St. Augustine a bit nicer, so I went back there. And during my postdoc, I also taught at the University of Bonn. And this institute with which there was a link between Fraunhofer and the University of Bonn was founded out of money which came from the Berlin Act. So now it turns out that Stuttgart also applied to be a capital of Germany in 1948. So if they have won, this link would not have been there. So it seems that already at 1948, things happened to make me come here to Stuttgart. Then I went to Bielefeld. Things became even more clear. My postdoc advisor, Philipp Semiano, actually studied as a minor subject at the IMS in Stuttgart. Then I started a company, and one of the co-founders of the company, the tall guy, Matthias Hartung, he actually lived in Stuttgart. So eventually, yeah, I needed to come to Stuttgart. So now I'm here since roughly 6 years. And a couple of months ago, I finished my habilitation, which now leads to this opportunity to give this lecture. And today I would like to link two topics. The one topic is what I did in my PhD, biomedical text mining, and the other topic is what I do in the last couple of years, structured modeling of affect in text. So everything I talk about today is about language understanding. So what is language understanding from my perspective? So the first thing is that we have language. And I typically work with text. I don't work with spoken language. So we have, for instance, Facebook posts, Twitter posts, or perhaps newspaper articles. And then we have a nice and friendly intelligent system which can do information extraction. So what does that mean? It means this friendly system, this machine should take the text, read the text, and then somehow distill the relevant information nuggets. If it just stays inside of the intelligent system, that's not too helpful. It could store these things inside of a database, which can then be helpful to access the information later and use this for downstream tasks. We could also take the structured information and generate language out of this. That's also something I'm interested in, but I'm just talking about this today. So challenges here are, on the one side, of course, the classical information extraction problem. We want to interpret and structure facts, knowledge, statements from text. But there's another thing that I would, broadly speaking, also see as information extraction, which is we have the text and we would like to infer information about the person who wrote this text. So we would like to infer properties about the author of a message. Now, this is this purple woman back here who wrote all these texts. And I look at two case studies, biomedical information extraction and emotion analysis today. So the goal of this lecture is, I would like to outline approaches to information extraction, highlight particularities of biomedical NLP and emotion analysis. Then I would like to highlight differences between different text genres, domains, and particular challenges. Discuss methodological implications for extraction tasks of different types. And at the end, I'll also tell you how these clearly pretty different fields like medical information and emotions could come together in applications and why it makes sense to look at both. So everything I talk about could be seen as concept identification. We have documents, texts, and we would like to know which concepts are mentioned in these documents. So for instance, if I learn that one of these documents contains concept 4, then in an information retrieval setting, I could say, I would like to have documents about concept 4, and we just return the documents which contain this. However, it could also be helpful to know where in this document concept 4 is mentioned. It can be helpful for further downstream tasks, additional information. And of course, one document can be linked to more than one concept. So what I'm doing here now is I'm mixing a couple of classical natural language processing tasks. I'm mixing named entity recognition, entity linking, normalization, and document classification here. And I do that such that I can talk about these different tasks somehow in a joint manner. So now I hope you're curious, and I'll get started with biomedical text understanding. So what is that? In BioNLP or medical NLP, often the term BioNLP is just used for everything that's somehow related to this. What we want to do is we would like to extract information from texts in the life science domain, broadly speaking. So, and the main motivation is that information could be considered to be hidden in text. So what does hidden mean? Hidden means it's either not easy to find it. It might be complicated to aggregate it, perhaps just because there's so much text that people couldn't read it. Yeah. So information might not be easily accessible in a structured manner. So that's what I mean with hidden. And there are many application scenarios. So for instance, I could aggregate information that's in scientific papers. For instance, this paper here is about COVID-19 and infection, and down here they talk about different cells that play a role there. Other cases could, for instance, be discharge letters. When somebody leaves the hospital, for instance, here we know that a person has been admitted to hospital with a complaint of chest pain, and then we see a set of different medical conditions that were also holding they were not holding. So different things that this person had in the past or currently has. And this can, of course, be interesting to find combinations of different medical conditions and how they come together, how they might influence each other. And there are many other cases, for instance, special cases like documentations of clinical trials, etc. And depending on the domain, there are different entity classes. So for instance, we could be interested to find gene names, mutation mentions, species. So what I have here now is a list of gene names which come from a website called What's Your Favorite Gene? And you see that these gene names are sometimes have a surprising linguistic realization. So it might be that when you find such names in text, that you would interpret it to be something else, actually. Yeah? There are chemical compounds which can be realized in different ways, like brand names or some systematic names. And there can be disease names, medical conditions, adverse effects, things like that. And what we want to find depends, of course, on the use case, on the domain, etc. So now let's just briefly look at one concrete example, which are chemical compounds, one of the topics from my PhD. So one idea could be that what you want to do now is you just check, okay, is there perhaps a database of the entity class that I would like to work with? So let's check for existing databases. So now I found this database, and in this database we have a list of different entity names that we are interested in. Then we could implement some dictionary matching algorithm, which should find entities in this database which occur in a document. And then we just find these mentions, link the mentions in the document to the elements in the text. And this would then directly allow us to find the entity in the database and additional information, because the database also has additional things, not just the entity name. Yeah, and this is actually what we did in 2008 with a set of colleagues, and I know that some of them are actually here. So I hope that you are not unhappy about me mentioning this paper. So now, yeah, this is what we did. And of course, the first question is, what are possible resources? And yeah, it turns out that there is a set of public resources for chemical names. I don't want to go into detail now, but we see that there is a set, and they have sometimes pretty sizes. Yeah. Now what we could do is we could just evaluate our fuzzy dictionary matching approach. We annotate the textual corpus. We mark all the entities in there that we're interested to find. Now we run our algorithm, let's say, with just a combination of all these different sources. And what happens is that we find this result. So depending on the actual realization of the chemical compound, we see that the recall can be really high. Yeah, it's really going up to 90%. For some names, this is not the case, but yeah, that can be solved in different ways. That looks promising. However, when we look at the precision, we see that this is really very limited. So we get with such a dictionary-based approach, we get a precision of 0.1 something. Yeah. Okay, that wasn't successful. Let's do an error analysis. So what do we find? Let's look at a couple of examples. So when we do this with chemical names, with this dictionary, which I just explained, what we find, for instance, is a document called Empowering Women Since 1912, the Girl Scouts of America. It's not chemical stuff, right? We find this one. I put this on the slide and then recognized that I wouldn't be able to pronounce it. So let's just move to the next one. Snow and ice ecosystems, not so extreme. So what happened here? Now, yeah, this dictionary is not perfect for our purposes. Huh? So there are compounds in there, for instance, like this one. Yeah, which is fine. I mean, this can be used for medical purposes, obviously. But when we look into the list of synonyms which we found in the entry of a chemical database, then we actually found things like girl and snow and so on. And I mean, of course, I didn't know that, but these are synonyms, actually street names for cocaine. But still they're in there. Now you could start to curate this resource to make it better, etc. But that's actually not what people do nowadays. What's a typical approach looks actually like that. So we typically take the documents. I mean, everybody can see me, right? I can also just point here. So what we typically do is we first start with taking the documents and then phrase the entity recognition task as sequence labeling, where we just label the sequence of words with belongs to an entity of interest or not. Yeah, 12 years ago, people used conditional random fields. 5 years ago, people used long short-term memory networks. Now everybody's using transformers. But the general task actually didn't change. The performance numbers, of course, went up. So when we found these different entities in text, then what we can do is we can just do dictionary mapping. We can just check for those where we are comparably sure that it's an entity. Is this in the dictionary? And then we can combine this, link this to the database. Another approach, which is particularly interesting in chemical names, is that you can also parse the internal structure of the names and reconstruct the chemical compound. There's a set of work in this direction. Actually, work on this topic has also happened in Stuttgart like 14 years ago. Uwe Reilet worked on this, right? When you do entity recognition, so this step here, then with a variation of a transformer bird, BioBird, which is fine-tuned to medical documents, then you actually get 92% F-score, which is a great result for chemical name recognition. But there are still open research topics. So people work on joint modeling for linking and named entity recognition together. That's something where the recent years didn't receive too much attention. In the recent years, this topic did not receive too much attention. And another interesting topic is also multitask learning between relations and entities. So now you could say, well, chemical names are a very special case. Does this also hold in other biomedical entities? So now when we look at disease names, for instance, it turns out that the patterns are essentially the same. So when we do that, we take a combination of dictionaries, check this, evaluate matching algorithm on paper abstracts, then we see that we acceptable recall, but a non-acceptable precision. However, there has been more or less recent work from 2013 by Robert Lehman who implemented a named entity recognizer who's jointly doing mapping to the database with a learning to rank approach. So it learns a preference function, which elements in the dictionary might be candidates to map to something that's in parallel found in the document. However, these names also have other challenges. So, for instance, with Camillo, who is also in the room, I've just seen this. So with Camillo, we checked is for the challenge of comparing disease names between scientific text and social media. And what we found there is that in social media, disease names are actually used in a pretty different way than in scientific text. And yeah, the main reason is that there are ambiguous synonyms in some dictionary entries. That's mostly the case for diseases which do not have a very dominant meaning for realization. Yeah? And then synonyms are also used in different ways. So this also forms one research direction. We are currently preparing a project where we aim at learning to align expert and layperson language, and one use case there is are disease names. So I'm nearly done with the first part of this talk. What we've seen so far is that biomedical information extraction is commonly formulated as machine-based named entity recognition, followed by a dictionary-based named entity normalization, and we could do relation extraction afterwards. Just wanted to mention that. The biomedical domain is characterized by comparably rich and high-quality resources. And there exists a rich set of different corpora, shared tasks where people can build models and evaluate their models. And one thing that I would like to point out is that in this task, we really have huge numbers of entities that we would like to find. So the challenge here is not so much that to find realizations in text concept, just one concept. The challenge is that there are so many concepts that we need to develop a system which finds these huge amounts of classes, potential concepts in text, though every separate classification is comparably straightforward. So if I build a classifier, does this document contain the concept of aspirin? I will probably have a very good classifier. The challenge is to do everything together. Yeah? And that's why this task is formulated as named entity recognition and normalization. This was mostly about scientific papers. However, there's also social media. Right? And I would like to argue that also in social media, there are interesting information nuggets in there. Yeah? So here we have a scientific document about COVID-19, and here we have a Twitter post about COVID-19, and the person is saying something, more or less the person is saying, I don't wear a mask because the virus doesn't exist. And the person does this in a very emotional language. So what I would like to claim now is that in scientific text, the important information nugget that I would like to extract are mostly facts, entities, relations. But in social media, it's also important to find information about the author, perhaps, properties about the author. And that brings me to the next part of this presentation, which is about text understanding regarding psychological concepts, particularly emotions. I only see two people in front of me, so it's really hard to know if everybody's happy. Do people look happy, Jonas? Okay, that's good. The chat looks also happy? Okay, good. You know that I download the chat afterwards and we'll just read it. Yeah. All right. So now we return to another concept, not away from biomedicine and to emotions. So now what we would like to do is we again have our intelligent system, and this system now should not directly extract facts from the text, but it should infer properties about the person who wrote these texts. And these are, for instance, personality traits. Is this person a friendly person, a hostile person, an extrovert, things like this? There might be categories like gender, nationality, age groups, things like this. And finally, emotions, stance, sentiment. Has the person been angry while writing a text, or perhaps does the person try to express joy, things like this? So to be able to do this, Of course, we first need to look into the conceptualization of emotions. In this chemical or disease field, I argued that there are resources. I don't need to really define what it is. I can just rely on the resource. But in emotions, that's a little bit more challenging. So what is an emotion? Emotions are, according to Scherer in 2005, an episode of interrelated, synchronized changes in the states of 5 organismic subsystems in response to an evaluation of a relevant stimulus event. So there's an event. I consider it is an important event, and that enables me or makes it necessary to develop an emotion. That's helpful. Yeah? Let's see how we can use this for text analysis. It's also helpful to think a little bit about emotion names. So for instance, Ekman came up with a list of 6 fundamental emotions: joy, anger, disgust, fear, sadness, and surprise. And he separated those, so he said these are fundamental emotions because you can just discriminate them by facial expressions. So it's something that can be observed. There are other sets of fundamental emotions, for instance, by Plutchik, that's so-called Plutchik wheel. I'm not going into detail, but it contains a set of more fundamental emotions. So now, what's the link between these models and events? So now let's say we have this person sitting on a chair, seeing a burning car. So that's an event, and the person might say, that's a burning car, that's relevant for me. Yeah, that's an event I need to care about. So now there are these different subsystems that now play a role. So the person develops a subjective feeling. Nervous, perhaps, a little bit, perhaps not so good. Yeah. So then there's an appraisal. So for instance, the person says, well, this could be dangerous for me. Yeah. So perhaps I should make sure that my house doesn't burn. Then there could be an expression. The person cries or shouts, or just the facial expression changes. There could be an action tendency, so the person could just run away or try to deal with the fire. And there could be a bodily symptom. The person could start to sweat because he's afraid or she's afraid. And now I'm hypothesizing that each of these different components could, in principle, lead to realizations in language. So each of these components could be used by an author of a novel or by somebody who's posting a social media post. Each of these components could be used to communicate an emotion. So what could this look like? Well, the person could just say, I feel bad, yeah, in a social media post. That would be using the subjective feeling. There could be a cognitive appraisal. It could be an expression. The person could describe an action tendency, or a novel author could describe bodily symptoms. Yeah. Or the person just mentions describes the event. There is a car on fire, and we all know that when a car is on fire, we should be afraid. So it's not necessary to describe in more detail what emotion the person feels, because we just agree, or the person assumes that we agree what the emotion is. So now, how do we find emotions in text? Yeah? Could we just use, for chemical compounds, we could just use, for each compound, we could just use a list of synonyms for this chemical compound. Could we do something like this here? Could we just use a list of synonyms for each emotion that we would like to find? Well, I just argued against that, right? Because there is a rich possibility to express emotions. So that might be challenging, so probably that's difficult. However, there are emotion dictionaries which exist. One popular one is the NRC dictionary, was mainly built by Saif Mohammed, and there are such words in the dictionary. For anger, for joy, or for sadness. And for each of the words, you could interpret, well, yeah, it makes sense somehow, but it wouldn't be too difficult to find examples where these words are used in a different context, right? So it wouldn't be sufficient to just find the word napkin in a document and decide this document is about sadness, right? You somehow need to have a more sophisticated aggregation algorithm. But that's and that's of course helpful, and it's a rich and valuable resource. But for classifying which emotion is expressed in a text, that might not be necessarily the best approach. So what do such systems look like? So let's say we have a Twitter post here. Somebody tweeted, "Wow, I'm so happy that I passed my habilitation." Hashtag emotion analysis. No, hashtag academic life, actually. And then we take this text and we put it into an emotion analysis system. And what we get out of this is, for instance, a categorical prediction that's about joy, perhaps also some other values. That's about classification. And now, when you remember how I talked about the biomedical concepts, I also said it might be sufficient to just find there's the concept in there, but it might also be helpful to find where it is in the text. And that's, in emotional analysis, a different task. So that's the task of semantic role labeling of emotion concepts, I would say. And here, the task could, for instance, be that we extract from the text above that the emotion is felt by somebody who's referenced with the word I. There's the word sequence "so happy," which helps me to understand which emotion is expressed. And there's also a stimulus, a cause, past my habilitation mentioned here. So that's in itself interesting to have additional information. I can analyze relations, for instance, between these things. That's an interesting and challenging task. And we developed a couple of different things there. So for instance, with Yevgeny, we developed a literature corpus, which we called "Who Feels What and Why." With Laura, we developed a news corpus, which she called "Good News, Everyone." And we also with Laura, we developed we compared different approaches to find such things in text. So token sequence labeling versus clause classification. And when you remember how we formulated the task of detecting a concept in the biomedical domain to a text, that what we typically do is we first find the words in the document and then associate this with the concept. This is a rather untypical approach in emotion analysis, but still what you could do is you could just first find these semantic roles and then see if this is perhaps sufficient to infer the emotion which is associated. Wasn't really clear if this is an approach which makes sense, so we evaluated this in a paper just very recently accepted, where we asked the question, which semantic roles enable machine learning to infer emotions? So this is about semantic role labeling, which again puts these segments in text together with the concepts that we would like to find. We also have this emotion component model, which I already mentioned, subjective feelings, expressions, event appraisal, etc. And the question, of course, is this perhaps helpful to know about this, to inform our classifier about these concepts? So I claim that this is additional information for downstream applications and helpful in itself. But we could also check if this actually supports emotion detection. And yeah, we looked into this. Is this really the case? Does classifying emotion components help? Perhaps all components play a role in each emotion, right? So how should that actually be helpful? So we wanted to know, can recognizing components contribute to emotion recognition? And this is something that Amelie Heindl and Felix Kaselt, who's a bachelor and a master student, did. And they looked into this in two different perspectives, on literature and on Twitter data. And what we found for Twitter data, are they actually here? Do you see them? Okay, so perhaps not. What we did is we annotated a corpus and checked for these different emotion components how they are distributed across the different emotions. And what we see that for Twitter, they are actually pretty similarly distributed. So when we just rank how frequently is each of these different components mentioned or used to communicate each of these different emotions, then the ranking would more or less be the same. So just the component itself will probably not be too helpful. Interestingly, on literature, that looks different. So in literature, the authors of texts seem to choose carefully which component they use to communicate an emotion. And perhaps not too surprisingly, mostly they use the violet appraisal. Yeah, so they describe an event, and we should just infer the emotion from the event description. But for some emotions, that's different. For instance, for anticipation, it's mostly about action tendencies. So if I see something coming, that will change how I behave. Yeah. For trust, we see that there's no neurophysiological reaction. I think there are some psychologists in the room. I wouldn't even know what neurophysiological reactions are to trust. And yeah, also interestingly, for anger, for instance, we also have motor expression. That's the most dominant component. So this might actually help to classify emotions. And what we see is that when we provide the component information to a classifier, to an emotion classifier, this doesn't help for Twitter, but it helps for literature. Yeah? When we do multitask learning of components and emotions together, that actually helps on both corpora. So it seems that the distribution is the same, but that there are still latent concepts that are shared between these different concepts. So yeah, back to my graph here. Now we are in the middle of the component process model, and part of this is the appraisal. And appraisal is an interesting concept, not too easy to grasp actually, but you can measure this with a set of different dimensions. So for instance, do you find an event pleasant? Do you feel that you are responsible for what's happening? Do you expect an increased effort to deal with the situation? Do you know what's going on? Are you certain about what's going on? Does it require your attention? Or do you feel like the situation just happened and I wasn't able to do anything about this? So this is by Smith and Ellsworth in 1985. They did a psychological study about this to detect these dimensions. And of course, the hypothesis now is that we perhaps shouldn't just do end-to-end learning. We have the emotion analysis system, we directly predict the emotion, but perhaps we better want to go this path here to predict the emotion with a model which is informed by these things. So I already talked a little bit about the component model. Now I talk about the appraisal. And this is the paper which we recently got accepted. So appraisal annotation. So the task was for our annotators, who are also in the room, so to answer the following question. Most probable, at the time when the event happened, the writer, which describes the event, wanted to devote further attention to the event, that's this attention dimension, was certain about what was happening, certainty, had to expend mental or physical effort to deal with the situation, that's effort, found that the event was pleasant, that's pleasantness, was responsible or felt responsible for the situation, responsibility, found that he or she was in control of the situation, or what we call circumstance, that the situation just took place and nobody was able to change this. So now we know what we want to annotate. Now the question is how we can do this. Yeah? So which corpus should we annotate? Yeah, we want events. We want to have an event-centered corpus. And yeah, it turned out that a year before we did this study, we built a event-focused emotion corpus for English and German, a crowdsourcing study, yeah, with Enrika and Sebastian. And this corpus was built by asking people on a crowdsourcing platform, remember an event which triggered concrete emotion name and describe it. I felt sadness when... So this led to 1001 event descriptions stratified by emotion. And these look like that. I felt sadness when I saw a homeless cat on the street. I felt shame when someone commented that I was looking very untidy. I felt anger when the police did not update me on a crime. And of course, the classification task in such corpus would be to predict the emotion without having access to these emotion names. So now we have a corpus. We post-annotated this with appraisal. And yeah, this what we see here now are radar plots, one for each emotion. And the dimensions in these radar plots are the appraisal dimensions. And there are some things in there that are really, straightforward. It totally makes sense. So for instance, the difference between anger and fear is mostly that in anger, you know what's going on, and in fear, you don't. Joy has the highest dimension for pleasantness. Yeah? And another thing that I find interesting is sadness has the highest, the most frequent elements that are associated with circumstance, which means the person wasn't able to change anything about the situation, which I think makes intuitive sense when it comes to sadness. Yeah? I think I should use more examples about joy. Okay. So now we have our annotated corpus, and now we would like to do some modeling experiments. So we compare our classifier, our emotion classifier, to one which just takes the text and predicts the emotion. Then we have one where we predict appraisal dimensions, multi-label problem from text, and an associated classifier which takes the appraisal and predicts the emotion. That could be run in a pipeline. Yeah. And then we also tried or looked into multitask learning of both concepts together. We used a convolutional neural network here for most of the tasks, except for the appraisal prediction, where we just use a fully connected two-layer neural network such that it can also exploit nonlinear relations between the appraisal dimensions to predict the emotion. And we evaluated via 10 times fault cross-validation. So first evaluation question, how well can we predict appraisal dimensions? Yeah, and what we get are numbers. Yeah, so it's not really clear if this is good or not, because nobody did this before, right? We don't know what we want to achieve actually, but it looks pretty reasonable. Attention and certainty gets above 80, precision, recall, and F. However, there are some dimensions, controls particularly, which is also a pretty complicated concept, I would say, where the scores are lower. But the actual question was, of course, can we use this now to predict emotions? So we compare this, we just look at the black columns here. So we predict, and we get a 60 F-score with our text to emotion classifier. That's a pretty typical result. You might say, well, 60 F-score is really low, but that's a pretty normal number that you get for emotion corpora. And now when we run our pipeline, first appraisal, then emotion, unfortunately, we were not able to get a higher result. Yeah, so that's research. Sometimes it's not successful. However, in principle, there is a potential to improve the result when we just use the appraisal dimensions to predict the emotion, which is knowledge known from psychology, but not necessarily that it's also possible when you post-annotate such a corpus. We see that we would be able to get a better result. So if we had a better appraisal classifier, we would be able to also increase the emotion classification. That's our assumption in the moment. For multitask learning, we didn't see an improvement. So now what we wanted to know is, could we perhaps combine this classifier and this classifier? Are there perhaps instances which are comparably easy to be classified with a direct emotion classifier, and perhaps there are instances which are better classified through the appraisal classifier? So we designed an oracle which always tells us which of the best classifiers will be better. That's something that you would replace later by an actual classifier. And what we get is a clear improvement. So this shows that these two methods here are complementary to each other. Yeah. So post-paper results show that, so we tried this, Jan tried this on also with the bird variation, and we see that the results actually get a boost by 10%, but the relations still don't. So still the text-based classifier is better. And yeah, so when we look at some errors, some examples, we also see that this approach seems to make sense. So let's just look at 2 or 3 examples. When we have the text, when I saw someone mistreating an animal, the text classifier says this is about disgust, probably because of the animal. Yeah. When we have the appraisal-based classifier, we actually correctly get anger, which is focusing on something else. When we have, because I ate a sausage that was horrible, the text classifier says shame. Shame is always about the self. Yeah. So that's the focus. This classifier that's what the classifier focuses on, while the appraisal-based classifier recognizes that it's about the horrible thing. And yeah, one of my favorite examples, when I was on a ferry in a storm and lots of people were vomiting, interestingly, the text-based classifier doesn't see the vomiting. Perhaps it's just not been there too often in the corpus. However, it recognizes storm, probably says this is about fear, while the appraisal classifier is able to correctly predict the emotion here. So what we've seen now is emotion classification directly from text remains the best approach, but we've seen that there is the potential to improve this. So this is actually promising. Yeah? The Oracle approach also showed that these different methods are clearly complementary. I shouldn't use difficult words. So, and in comparison to the biomedical case, again, what we have here are comparably few concepts, right? And that is why the most straightforward idea is to just tackle this as a standard text classification approach, optionally enriched and modeled jointly with segments. So what we will do in the emotion analysis in the future is we increase the data, the corpus, yeah, a large scale resource where we directly get appraisal labels. We don't post annotate them. We'll also look into annotations of structured event representations, not only linguistic realizations. And we'll explore other model architectures, of course. So we're not really done with this yet. We have a DFG project on this called SEED. And this starts in January 21 with Laura as a soon-to-be postdoc. And yeah, we also still work on role labeling, of course. With Karina, we prepare a DFG project where we combine images and text. And we are also still on joint modeling of roles with emotion prediction. So that's the end for the emotion classification part. Still everybody happy? Tell me when somebody looks unhappy, then I'll tell more jokes. All right, so now I talked about two pretty different topics. I talked about biomedical entities and emotions. So let's look at this again. In the biomedical information extraction field, we have many entities that we would like to find, and each of them has comparably few linguistic realizations, yeah? At least compared to other concepts. There are huge databases available, which are also pretty established. And I would say the main challenge is the precision in predicting things. In emotional analysis, we have just very, very few concepts to link. I mean, if it's many, then perhaps 20 or 30, right? But typically just less than 10. But each of them has many different linguistic realizations. And another challenge is that the conceptualization is also still under constant discussion. It seems that not everybody agrees what an emotion is, what we want to find as an emotion, etc. So I would say precision and recall are both challenging here. So why do I care about both? So on the one side, emotions can be seen as a fact. When I analyze social media, emotions are things that people talk about. They mention, I feel this and that because of this and that. So that's not necessarily something implicit. It can also be seen as a fact. And this is interesting, for instance, when we want to analyze public health, public well-being, quality of life of individuals or peoples. On the other side, emotions can be seen as a factor. So when I do extract, for instance, facts, biomedical facts, for instance, I could see emotions as a factor, for instance, for misinformation, disinformation, and use this as a signal for fact-checking. And yeah, this is also something where we put these things together. We have a new DFG project starting in January with Amelie Würl as a PhD student on biomedical fact-checking. So now, yeah, I already talked a little bit about the future, but I still want to say a couple of words about what I plan to do in the future. So what I want to do in the long term is I would like to make accessible and understand the communication of relational information, perhaps with a focus on biomedical information, across different sources, scientific text, social media, but also about, between experts and lay people, between different groups. And further, do the same thing with psychological concepts like emotions, across different domains, modalities, ways how they are realized. And I hope that I made clear now in this presentation how these two different topics can also come together. So I would also like to link medical information and psychological concepts, what I call now as they occur in the wild. So when people on social media talk about medical things, this should be linked with psychological concepts. That's what I claim, and I see upcoming work in the next years in this direction. Yeah, and finally, of course, today I only talked about phenomena, not so much about methods. Of course, we need to develop resources for that. We need to develop machine learning methods for that. So that's not something where always just running a black box system will help. I would also just briefly like to state a couple of ethical considerations, because some of them, especially in the emotion case, that might be pretty challenging. So systems that we develop clearly suffer from biases. This bias comes from input encodings, it comes from corpora, it comes from annotations. So that also means that these systems are not necessarily reliable. And further, corpora and systems do not represent all groups in a population equally. So I must say, I just recently understood that this is the reason why we always need to report in quite some detail who annotated a corpus. So it's important that we make very clear how a corpus annotation might be depending on property annotators. And finally, especially in the emotion case, it might be that we analyze concepts that somebody is expressing without not knowing that they currently feel a special emotion, that they express this concept. So they don't know that they feel a special emotion, and they don't know that they express it. And I think in the case that we uncover something from a social media post that the person doesn't know that we uncover it, or even the person doesn't know that the person is currently having a special emotion, I find it would be very questionable ethically. Yeah? So one conclusion could be that we should never infer any information about individuals, but only report results in an aggregated form, if this is possible, or at least we should be aware of this. So yeah, that's it for me today. I wrote here, please type Q in the chat if you have a question. I thought that I would be able to see the chat, but yeah, everything turned out a bit differently, but perhaps we can still do it like that. Yeah, thank you very much. So should I turn on the speaker here now, or?